We begin with a single molecule of cocoa butter. This molecule is a triglyceride. 3 fatty acid chains attached to a glycerol backbone. The specific fatty acids in cocoa butter are stearic acid, palmitic acid, and oleic acid, arranged in thermodynamics, particular combinations. The molecule is 2.5 nanometers long. If you lined up 4 million of these molecules end to end, they would stretch 1 centimeter. In a 100-gram bar of chocolate, there are approximately 30 trillion of these molecules. At room temperature, 20 degrees Celsius, these molecules are solid. They pack together in an organized structure called a crystal lattice. But cocoa butter can form 6 different crystal structures, numbered form Y through form 6. Form I melts at 17 degrees Celsius. Form 2 melts at 23 degrees. Form 3 melts at 26 degrees. Form FUI melts at 28 degrees. Form VI melts at 34 degrees. Form 6 melts at 36 degrees. Only Form VI produces good chocolate. Form VI crystals are stable, compact, and regular. They create chocolate that is glossy, hard, and snaps cleanly when broken. Form V chocolate melts smoothly at body temperature, 37 degrees, which is why it melts in your mouth. The other forms produce bad chocolate. Form I, 2, and the 3 are too soft. They melt at room temperature, leaving chocolate sticky and shapeless. Form I4 is brittle and crumbly. Form C is too hard and doesn't melt properly in the mouth. The molecular arrangement in Form Phi is specific. The triglyceride molecules stack parallel to each other, like books on a shelf. The fatty acid chains align, creating a regular repeating pattern. The spacing between molecules is 0.46 nanometers. This precise spacing is what gives Form V its unique properties. In Form A4, the spacing is 0.48 nanometers, just 0.02 nanometers different. This tiny difference changes everything. Form IV crystals are less stable and have different mechanical properties. They're harder, but more brittle. They lack the smooth mouthfeel of Form V. The challenge of chocolate making is controlling which crystal form develops. When melted chocolate cools naturally, it forms a mixture of all 6 forms. The result is chocolate with a dull grey surface, a crumbly texture, and a waxy mouthfeel. This is called bloom. To prevent bloom, the chocolate must be tempered. Tempering is a controlled heating and cooling process that ensures only Form V crystals develop. The process requires precise temperature control, accuracy within 0.5 degrees Celsius. The tempering process begins in a machine called a tempering unit. This machine consists of several components: a melting tank, a cooling jacket, a heating element, temperature sensors, and a mechanical stirrer. The melting tank holds 500 kilograms of chocolate. The chocolate arrives as solid blocks called pistoles, small, disc-shaped pieces approximately 1 centimeter in diameter and 3 millimeters thick. The pistoles are poured into the tank, filling it to 80% capacity. The remaining 20% is left empty, to allow room for expansion and to prevent overflow during stirring. The heating element is a series of electrical resistance coils embedded in the tank walls. When electrical current flows through these coils, they heat up due to resistance. The heat transfers through the metal wall into the chocolate. The coils are arranged in zones: bottom zone, middle zone, and top zone, each controlled independently. The temperature is monitored by platinum resistance thermometers, sensors that change electrical resistance based on temperature. Platinum is used because its resistance changes linearly with temperature and it's stable over many years of use. These sensors are accurate to 0.1 degrees Celsius. There are 3 sensors, one at the top of the tank, one in the middle, one at the bottom. The readings from all 3 sensors are averaged by a computer controller. This controller is a PLC, programmable logic controller, running software specifically designed for chocolate tempering. If the average temperature is below the set point, the heating elements activate. If it's above, they deactivate. This on-off cycle maintains temperature within 0.5 degrees of the set point. The stirrer is a large paddle that rotates at 20 revolutions per minute. The paddle is made of stainless steel, shaped like a ribbon, twisted into a helix. It extends from the top of the tank to the bottom and from the center to within 2 centimeters of the walls. As it rotates, it moves chocolate from the bottom to the top and from the center to the edges. This movement serves 2 purposes. First, it ensures even temperature distribution. Without stirring, the chocolate near the heating elements would be hot, while the chocolate far from the elements would be cool. The temperature difference could be 10 degrees or more. Second, it prevents the chocolate from burning on the hot tank walls. Even though the walls are only heated to 50 degrees, stationary chocolate in contact with them would develop a burnt layer. The stirrer must move continuously. If it stops for even 5 minutes, the chocolate begins to settle, and a thick layer forms at the bottom. This layer insulates the chocolate above it from the heating elements, making temperature control impossible. The first stage of tempering is melting. The temperature is set to 50 degrees Celsius. At this temperature, all 6 crystal forms melt completely. The chocolate transitions from solid to liquid. This transition is not instantaneous. It takes approximately 90 minutes for 500 kilograms of solid chocolate pistoles to become completely liquid at 50 degrees. During this time, the stirrer rotates continuously, breaking up clumps and distributing heat. The melting happens in stages. First, the pistoles in contact with the tank walls begin to soften. Their surfaces become sticky. As the stirrer moves through them, it breaks them apart. The broken pieces have more surface area, so they melt faster. After 30 minutes, the chocolate is a slurry, a mixture of liquid and solid. The liquid chocolate has a viscosity of about 1,000 centipoise at 50 degrees. It flows like heavy cream. The solid pieces float in this liquid, slowly dissolving. After 60 minutes, 80% of the chocolate is liquid. Only the largest pieces remain solid, pieces that were in the center of the pile, farthest from the heating elements. These pieces are now small enough that the stirrer breaks them apart easily. After 90 minutes, the chocolate is completely liquid. There are no visible solid pieces. But there may still be tiny crystal fragments, clusters of perhaps 100 or 1,000 molecules that haven't fully dissolved. These fragments are too small to see, but large enough to affect tempering. The melting process requires energy. To melt 1 kilogram of chocolate requires 160 kilojoules of energy, equivalent to the energy needed to lift that kilogram 16 kilometers straight up against gravity. For 500 kilograms, that's 80 megajoules, or 22 kilowatt-hours of electrical energy. At a typical industrial electricity rate of 0.12 per kilowatt-hour, that's 2.64 in electricity cost just for melting. Once fully melted, the chocolate is held at 50 degrees for 30 minutes. This holding period ensures complete melting. Any remaining crystal fragments dissolve. The chocolate is now a homogeneous liquid, containing no crystal structure whatsoever. All the triglyceride molecules are moving randomly, tumbling and sliding past each other. The second stage is cooling. The temperature set point is lowered to 27 degrees Celsius. Cold water flows through the cooling jacket, a hollow space in the tank walls. The water enters at 10 degrees and exits at 18 degrees, having absorbed heat from the chocolate. The cooling jacket is a double-wall construction. The inner wall is in contact with the chocolate. The outer wall is exposed to room air. Between them is a 2-centimeter gap through which water flows. The water flows in a serpentine path, entering at the bottom, spiraling upward, and exiting at the top. The cooling rate is controlled by adjusting the water flow rate. For slow cooling, the water flows at 10 liters per minute. For fast cooling, 50 liters per minute. For this tempering process, the flow rate is set to 25 liters per minute, giving a cooling rate of approximately 1 degree per minute. The chocolate cools from 50 degrees to 27 degrees in 23 minutes. Too fast, and undesirable crystal forms develop. Too slow, and the process takes too long, reducing productivity. The 1 degree per minute rate is optimal, fast enough for efficiency, slow enough for quality. As the temperature drops, the cocoa butter molecules slow down. At 50 degrees, they move rapidly, constantly shifting position. Their kinetic energy is high enough to overcome the attractive forces between molecules. They're free to tumble and rotate. At 40 degrees, they move more slowly. The kinetic energy has decreased. The attractive forces, van der Waals forces, can now hold molecules together briefly before thermal motion breaks them apart. Small clusters form and dissolve in milliseconds. At 35 degrees, just above the form Vi melting point, the molecules spend more time attached than detached. Clusters of 10 or 20 molecules persist for seconds, but these clusters are still transient. They don't grow into stable crystals because the thermal energy is still high enough to break them apart. At 27 degrees, the molecules begin to arrange themselves into crystals. This is called nucleation. A small cluster of molecules, perhaps 100 or 200, spontaneously arrange into an ordered pattern. This cluster becomes a seed crystal. Nucleation is a random process. It can happen anywhere in the liquid, at any time. The first nucleus might form in the center of the tank, or near the wall, or near the surface. There's no way to predict where or when. Once a nucleus forms, it can grow or dissolve. If the local temperature is too high, the nucleus dissolves. The thermal energy breaks it apart. If the temperature is right, the nucleus grows, more molecules attach to its surface. The crystal form that develops depends on temperature. At 27 degrees, primarily form Fo and form V crystals nucleate. These are the most stable forms at this temperature. The other forms are thermodynamically unfavorable and don't form. However, form Phi and form V crystals look identical at this stage. Both are stable at 27 degrees. Both will grow if given the opportunity. The goal is to encourage form V and discourage form V. This is accomplished through seeding. At 27 degrees, the operator adds a small amount of pre-tempered chocolate to the tank, approximately 1% by weight, or 5 kilograms for a 500 kilogram batch. This seed chocolate contains billions of form V crystals. The seed chocolate was made previously using the same tempering process. It was then cooled to room temperature and stored. When added to the liquid chocolate, these crystals don't melt because the temperature is below form V's melting point of 34 degrees. Instead, they remain solid and act as templates. The seed chocolate is added while the stirrer is running. The stirrer breaks the seed chocolate into small pieces and distributes them throughout the tank. Within 2 minutes, the form V crystals are evenly dispersed. The liquid cocoa butter molecules are attracted to the surface of these seed crystals. They attach to the crystal surface, adding one layer at a time. The seed crystal grows, incorporating more molecules in the same form Vi pattern. The attachment process is selective. Only molecules oriented correctly can attach. A molecule approaching the crystal surface must align its fatty acid chains parallel to the chains already in the crystal. If it's misaligned, it bounces off. The probability of correct alignment depends on temperature. At 27 degrees, about 1 in 1,000 molecular collisions results in attachment. This may seem inefficient, but with billions of molecules colliding with the crystal surface every second, the growth rate is still significant. This growth is exponential. One seed crystal becomes larger. As it grows, its surface area increases, so more molecules can attach simultaneously. A crystal that gains 1,000 molecules per second initially will gain 2,000 per second once it doubles in size. Additionally, the seed crystals themselves can break apart. As the stirrer rotates, it creates shear forces that can fracture crystals. A crystal that breaks in half becomes 2 separate seed crystals, each capable of growing independently. Within 10 minutes of adding seed chocolate, there are billions of form V crystals distributed throughout the 500 kilograms of chocolate. These crystals are still microscopic, perhaps 0.1 micrometers in size, but they're present in enormous numbers. The third stage is warming. The temperature is raised to 31 degrees Celsius. This temperature is critical. It's above the melting point of form 4, 28 degrees, but below the melting point of form V, 34 degrees. At 31 degrees, any form 4 crystals that formed during cooling now melt. They dissolve back into liquid. The triglyceride molecules that were locked in the form Phi crystal structure are now free again. But form V crystals remain solid. This selective melting purifies the crystal population, leaving only form V. The warming is gradual, about 0.5 degrees per minute, taking 8 minutes to go from 27 to 31 degrees. Gradual warming is important. If the temperature rises too quickly, 2 or 3 degrees per minute, the temperature near the heating elements might spike to 33 or 34 degrees, melting some form V crystals. The chocolate is held at 31 degrees for 20 minutes. During this time, the shea stirrer continues rotating, distributing form V crystals evenly throughout the tank. The chocolate is now tempered. It contains billions of form V seed crystals suspended in liquid cocoa butter. This tempered chocolate must be used within 4 hours. After 4 hours, the form V crystals grow too large. A crystal that starts at 0.5 micrometers grows to 5 or 6 micrometers. When chocolate contains very large crystals, it becomes grainy. The ideal crystal size is 0.5 to 1.0 micrometers, half a thousandth of a millimeter. Crystals larger than 5 micrometers are perceptible to the tongue as grittiness. The growth rate at 31 degrees is approximately 0.001 micrometers per minute. A 0.5 micrometer crystal grows to 1.7 micrometers in 2 hours and to 2.9 micrometers in 4 hours. Beyond 4 hours, the crystals are too large for optimal quality. The tempered chocolate flows from the tempering tank through a heated pipe to the enrober. The pipe is 5 centimeters in diameter and 3 meters long. It's heated to 31 degrees by electrical heating tape wrapped around the exterior. The heating tape is a flexible ribbon containing resistance wire. When plugged in, the wire heats up. The pime tape is wrapped in a spiral around the pipe, with wraps spaced 2 centimeters apart. A thermostat monitors the pipe temperature and turns the heating tape on or off to maintain 31 degrees. The pipe slopes downward at a 2-degree angle, about 10 centimeters of drop over 3 meters. This slope ensures chocolate flows by gravity. Without the slope, a pump would be needed, and pumps can damage chocolate by creating excessive shear forces that break crystals. The chocolate flows at approximately 20 liters per minute. At this flow rate, the pipe is about 40% full. The chocolate forms a stream along the bottom of the pipe with air above it. This partial filling is intentional. It prevents pressure buildup that could cause splashing when the chocolate exits the pipe. The enrober is a machine that coats food items with chocolate. It's 4 meters long, 1.5 meters wide, and 2 meters tall. The machine consists of several sections: the chocolate reservoir, the curtain, the wire belt, the blower, and the cooling tunnel. The chocolate reservoir is a stainless steel tank at the bottom of the enrober. It holds 200 kilograms of tempered chocolate at 31 degrees. The tank is 1.5 meters long, 1 meter wide, and 20 centimeters deep. The bottom is sloped toward one end where a drain valve is located for cleaning. The tank has a heating element that maintains 31 degrees precisely. The element is a coiled resistance wire encased in a copper tube mounted to the tank bottom. The copper tube protects the chocolate from direct contact with the hot wire, which could cause burning. The chocolate is stirred continuously by a small paddle rotating at 30 revolutions per minute. This paddle is much smaller than the tempering tank paddle, only 30 centimeters in diameter. It's positioned near the pump intake to ensure the chocolate being pumped is well mixed and free of settled particles. From the reservoir, chocolate is pumped upward through a pipe to the curtain mechanism. The pump is a positive displacement pump, specifically a lobe pump. It has 2 figure-8-shaped rotors that mesh together and rotate. As they rotate, they trap chocolate between the lobes and the pump housing, pushing it forward. Lobe pumps are used because they're gentle. They don't create the high shear forces that centrifugal pumps do. High shear can damage chocolate by breaking fat crystals and creating heat through friction. The pump speed is adjustable from 0 to 100 liters per minute using a variable frequency drive that controls the motor speed. For this application, the pump runs at 40 liters per minute. This flow rate creates a chocolate curtain of the right thickness. Too slow, and the curtain becomes too thin and breaks into droplets. Too fast, and the curtain is too thick, creating heavy, uneven coatings. The curtain mechanism is at the top of the enrober, 1 meter above the wire belt. It consists of a horizontal pipe with a slot cut along its length. The slot is 60 centimeters wide and 2 millimeters tall. The pipe is fed by the pump, so it's always full of chocolate under pressure. The chocolate flows through the slot, creating a falling curtain of liquid chocolate. The curtain is 60 centimeters wide enough to coat items up to 50 centimeters across. The 2 millimeter slot creates a curtain about 3 millimeters thick after it falls and spreads slightly. The curtain falls vertically at approximately 2 meters per second. This falling speed is determined by gravity. All objects fall at 9.8 meters per second squared. After falling 1 meter, an object reaches a velocity of about 4.4 meters per second. But the chocolate curtain experiences air resistance that slows it to about 2 meters per second. The curtain flow is laminar, flowing in smooth parallel layers, with no turbulence. Turbulent flow would introduce air bubbles, which create defects in the coating. Air bubbles look like tiny pinholes in the finished chocolate surface. To maintain laminar flow, the slot must be perfectly straight and smooth. Any irregularity, a burr, a scratch, a dent, creates turbulence. The slot edges are polished to a mirror finish, with roughness less than 0.1 micrometers. Below the curtain is the wire belt, a conveyor made of thin stainless steel wires woven into a mesh. The wires are 0.5 millimeters in diameter, woven with a spacing of 3 millimeters between wires. This creates openings through which excess chocolate can drip. The belt is 60 centimeters wide and 6 meters long, running in a continuous loop over 2 drums. A drive drum at one end and an idler drum at the other. The drive drum is powered by an electric motor with a reduction gearbox. The motor is 0.75 kilowatts, running at 1,400 revolutions per minute. The gearbox reduces this to 20 revolutions per minute at the drum. The belt moves at a speed of 10 meters per minute, or 16.7 centimeters per second. This speed is carefully chosen. Too slow, and production rate is low. Too fast, and the chocolate coating doesn't have time to drip to the proper thickness. The belt tension is critical. Too loose, and the belt sags and rubs on the frame. Too tight, and the belt stretches and eventually breaks. The tension is adjusted by moving the idler drum position. A spring-loaded mechanism maintains constant tension as the belt expands and contracts with temperature changes. Food items to be coated, cookies, nuts, caramel centers, are placed on the belt before it enters the enrober. The items are placed by hand by an operator standing at the belt entrance, or by an automated feeding system. For hand placement, the operator picks items from a tray and places them on the belt with consistent spacing, about 5 centimeters between items. The spacing is important. If items are too close together, chocolate bridges between them, joining them. If too far apart, production rate is low. For automated feeding, items arrive on another conveyor that transfers them onto the enrober belt. The transfer timing is controlled by sensors that detect belt position and item position, ensuring items land on the belt at the right spot. The items travel under the chocolate curtain. As they pass beneath, chocolate pours over them, coating the top and sides. The chocolate flows down over the edges, meeting underneath and coating the bottom. Excess chocolate drips through the wire mesh and falls back into the reservoir. The thickness of the coating depends on several factors: chocolate viscosity, belt speed, and curtain flow rate. For a typical coating 2 millimeters thick, the belt speed is 10 meters per minute and the pump speed is 40 liters per minute. Chocolate viscosity is critical. Viscosity is resistance to flow, how thick the liquid feels. Water has low viscosity, 1 centipoise at 20 degrees, and flows easily. Honey has high viscosity, 10,000 centipoise, and flows slowly. Chocolate's viscosity depends on temperature and composition. At 31 degrees, dark chocolate has a viscosity of approximately 2,000 centipoise. This is about twice the viscosity of motor oil. Milk chocolate is slightly higher, 2,500 centipoise, because milk proteins increase resistance to flow. White chocolate is higher still, 3,000 centipoise, because it contains no cocoa solids, only cocoa butter, and the higher fat content paradoxically increases viscosity. If viscosity is too high, the chocolate doesn't flow smoothly over the items. It creates thick, uneven coatings with visible drip marks. If viscosity is too low, the coating is too thin and doesn't cover the item completely. There may be bare spots where the underlying item shows through. Viscosity is adjusted by adding cocoa butter or lecithin. Cocoa butter reduces viscosity. Adding 1% cocoa butter, 5 kilograms to a 500 kilogram batch, reduces viscosity by approximately 10%, from 2,000 to 1,800 centipoise. Lecithin is more effective. Lecithin is a phospholipid extracted from soybeans. Its molecules have one hydrophilic, water-loving end, and one hydrophobic, water-hating end. In chocolate, lecithin molecules arrange themselves at the interface between cocoa butter and sugar particles. Chocolate is a suspension, solid sugar particles suspended in liquid cocoa butter. The sugar particles rub against each other as the chocolate flows, creating friction. Lecithin coats the sugar particles, reducing this friction. Adding 0.3% lecithin, 1.5 kilograms per 500 kilograms, reduces viscosity by 15%, from 2,000 to 1,700 centipoise. Too much lecithin causes problems. Above 0.5%, the chocolate becomes too fluid, and the coating runs off the items before solidifying. The optimal lecithin concentration is 0.3 to 0.4%. After passing under the curtain, the coated items continue on the wire belt through the blower section. The blower is a row of air knives, thin slots that direct high-velocity air onto the chocolate surface. There are 6 air knives positioned across the belt width, each 10 centimeters long with a 2 millimeter slot. The knives are positioned 10 centimeters above the belt, angled at 45 degrees, pointing in the direction of belt travel. Each air knife is fed by a centrifugal blower, a fan that creates high-pressure air. The blowers are 2 kilowatts each, running at 3,000 revolutions per minute. Together, the 6 blowers move 600 cubic meters of air per hour. The air exits the knives at 30 meters per second, about 108 kilometers per hour. This high-velocity air shears off excess chocolate, creating a smooth, even coating. The sheared chocolate falls back into the reservoir through the wire mesh. The air knives also help with temperature control. The chocolate-coated items emerge from under the curtain at 31 degrees. The blower air is at 18 degrees, room temperature. This 13-degree difference begins the cooling process. The cooling must be gradual. If the chocolate cools too quickly, dropping from 31 to 20 degrees in 1 minute, Form V crystals don't have time to grow properly. The chocolate solidifies before the crystals reach optimal size, resulting in a dull surface and soft texture. From Saishwaram, the blower items enter the cooling tunnel. This tunnel is 3 meters long, 60 centimeters wide, and 40 centimeters tall. It encloses the belt completely, creating a controlled environment. The tunnel is refrigerated to 10 degrees Celsius. The cooling is provided by a refrigeration system mounted above the tunnel. Cold air is blown downward from slots along the tunnel ceiling, flows through the wire mesh and around the coated items, and exits through slots along the tunnel sides. The airflow rate is 1,200 cubic meters per hour. This creates an air velocity of about 1 meter per second around the items. Fast enough for good heat transfer, slow enough that it doesn't disturb the chocolate coating. The cooling rate is carefully controlled. The chocolate must cool from 31 degrees to 20 degrees in approximately 10 minutes. This cooling rate, about 1 degree per minute, allows Form V crystals to grow to optimal size. The belt spends 3 minutes traveling through the tunnel. During this time, the chocolate surface temperature drops from 31 to about 22 degrees. The interior of the coating is still warmer, perhaps 26 degrees, but the surface is solid enough that the items can be handled without smudging. If cooling is too fast, more than 2 degrees per minute, the chocolate develops thermal shock. The surface contracts faster than the interior, creating stress. This stress appears as cracks in the coating, fine lines that run across the surface, compromising appearance and allowing moisture to penetrate. If cooling is too slow, less than 5 degrees per minute, the chocolate stays liquid too long. Form V crystals grow very large, creating graininess. Also, untempered chocolate from the interior can migrate to the surface and bloom. The cooling tunnel maintains 10 degrees with a variance of plus or minus 1 degree. This is achieved using a closed-loop refrigeration system, a cycle that continuously removes heat from the tunnel air. The refrigeration system uses R404A refrigerant. This is a blend of 3 hydrofluorocarbons, R125, 44%, R143A, 52%, and R134A, 4%. The blend was formulated to have the right thermodynamic properties for this temperature range, efficient heat removal at 10 degrees. The refrigerant circulates through 4 components arranged in a closed loop: evaporator, compressor, condenser, and expansion valve. In the evaporator, liquid refrigerant absorbs heat from the tunnel air. The refrigerant boils at 0 degrees at the operating pressure. So when 10-degree air flows over the evaporator coils, heat transfers from air to refrigerant. The air cools to 8 degrees and is blown into the tunnel. The refrigerant evaporates, becoming a gas. The gaseous refrigerant flows to the compressor. The compressor is a scroll compressor, 2 spiral-shaped scrolls, 1 stationary and 1 orbiting. As the orbiting scroll moves, it traps gas between the scrolls and pushes it toward the center, compressing it. Compression increases pressure from 3 bar to 15 bar and increases temperature from 0 degrees to 60 degrees. The hot, high-pressure gas flows to the condenser. The condenser is a heat exchanger where refrigerant releases heat to outside air. Room air at 20 degrees is blown over the condenser coils by fans. Heat transfers from the 60-degree refrigerant to the 20-degree air. The refrigerant cools and condenses back into liquid at 40 degrees. The liquid refrigerant flows to the expansion valve. This valve is a small orifice that restricts flow. As refrigerant passes through, pressure drops from 15 bar to 3 bar. This pressure drop causes temperature to drop from 40 degrees to 0 degrees. The cold liquid returns to the evaporator, completing the cycle. This cycle runs continuously, removing approximately 15 kilowatts of heat from the tunnel, equivalent to the heat output of 15 electric space heaters. This heat comes from 2 sources: the chocolate itself, as it cools, and heat leaking through the tunnel walls from the warmer outside environment. The heat from chocolate is significant. Each kilogram of chocolate releases 160 kilojoules as it cools from 31 to 20 degrees and crystallizes. For 200 kilograms per hour of production, that's 32 megajoules per hour, or 8.9 kilowatts. As the chocolate-coated items move through the cooling tunnel, the chocolate solidifies. The Form V crystals grow, connecting into a 3-dimensional network. Individual crystals that were 0.5 micrometers at the tunnel entrance grow to 1.0 micrometers at the exit. These crystals don't grow in isolation. As one crystal grows, it depletes the liquid around it of triglyceride molecules. Eventually, growing crystals touch each other. When they touch, they form a continuous network spanning the entire chocolate mass. This network gives the chocolate its structure, its hardness, its snap, its gloss. The network is about 60% crystal and 40% liquid cocoa butter trapped between crystals. The trapped liquid gives chocolate its smooth mouthfeel. When you eat chocolate, this liquid is released as the crystal network breaks apart in your mouth. At the end of the cooling tunnel, the chocolate is solid. The temperature is 15 degrees. Cool enough that the coating is hard and won't smudge when touched, but still slightly soft in the interior. The items exit onto a collection conveyor where they continue cooling to room temperature over the next 10 minutes. The quality of chocolate is determined by its crystal structure. Well-tempered chocolate contains billions of tiny Form V crystals, all approximately the same size and all oriented in the same direction. These crystals are organized and uniform. When you break well-tempered chocolate, it snaps cleanly with a sharp sound. This snap is the sound of crystal lattices fracturing. The fracture propagates through the chocolate at approximately 1,000 meters per second, faster than the speed of sound in air, 340 meters per second. The fracture begins at a stress concentration, a point where internal stress is highest. This might be a corner, an edge, or a surface defect. When you apply force by bending the chocolate, stress concentrates at these points. When stress exceeds the crystal bond strength, about 50 megapascals for Form V cocoa butter, the bonds break. The fracture starts at a single point and spreads rapidly. The fracture front moves through the crystal network, breaking bonds as it goes. The fracture follows crystal boundaries, the interfaces between individual crystals. Because the crystals are small and uniform, all about 1 micrometer, the fracture path is straight and clean. The broken edge is smooth and glossy. You can see your reflection in it. The sound of the snap is created by the rapid release of energy. When bonds break, energy stored in the stressed crystal lattice is suddenly released. This energy travels through the chocolate as a shock wave, a rapid pressure pulse that propagates at the speed of sound in chocolate, approximately 2,000 meters per second. When this shock wave reaches the surface, it creates vibrations in the air, sound waves. The frequency of these vibrations determines the pitch of the sound. Well-tempered chocolate produces frequencies around 3,000 to 5,000 hertz, a sharp, high-pitched crack. Poorly tempered chocolate doesn't snap. It bends or crumbles. This is because the crystals are large and irregular. Large Form 4 or Form 6 crystals can be 10 or 20 micrometers, 10 to 20 times larger than Form V crystals. When you try to break chocolate with large crystals, the eye fracture path wanders around these large crystals rather than cutting through them. The path follows the long way around, making the fracture slower and requiring more energy. The result is bending instead of snapping. If the chocolate does break, it crumbles. The fracture splits into multiple paths, creating many small fragments, instead of 2 clean pieces. The broken edge is rough and dull, not smooth and glossy. The gloss of chocolate also depends on crystal structure. Gloss is the mirror-like reflection of light from a smooth surface. The smoother the surface at the microscopic level, the glossier it appears. Well-tempered Form V chocolate has a surface roughness of about 0.2 micrometers. This is measured using a profilometer, an instrument that drags a diamond stylus across the surface and measures vertical displacement. A roughness of 0.2 micrometers is smooth enough that light reflects uniformly, creating gloss. Poorly tempered chocolate has surface roughness of 5 micrometers or more. At this roughness, light scatters in different directions rather than reflecting uniformly. The surface appears dull, sometimes even whitish. The mechanism of gloss is interesting. Light hits the chocolate surface at many different angles. If the surface is smooth, all reflected light travels in one direction. The specular direction, where angle of reflection equals angle of incidence. Your eye sees this reflected light as gloss. If the surface is rough, reflected light scatters in many directions. Some light goes toward your eye, but most goes elsewhere. The total amount of light reaching your eye is less, so the surface appears dull. Form V crystals pack more efficiently than other forms. They occupy 3% less volume than Form IV crystals. This contraction during crystallization is important, causes chocolate to shrink slightly as it solidifies. This shrinkage is why chocolate releases easily from molds. When liquid chocolate is poured into a mold and allowed to crystallize, the solid chocolate contracts and pulls away from the mold walls. A gap forms, typically 0.1 to 0.2 millimeters wide. When the mold is inverted, the chocolate falls out cleanly. Without this shrinkage, chocolate would stick in the mold. You'd have to flex the mold or tap it vigorously to release the chocolate. The chocolate surface would be damaged, scuffed, or scratched from the release process. The shrinkage is approximately 2% by volume. For a 100-gram bar of chocolate occupying 60 cubic centimeters when liquid at 31 degrees, the volume decreases to 58.8 cubic centimeters when solid at 20 degrees. This 1.2 cubic centimeter difference creates the gap between chocolate and mold. The shrinkage happens gradually as the chocolate cools and crystallizes. At 31 degrees, the chocolate is liquid and fills the mold completely. At 28 degrees, crystals begin forming, But the chocolate is still mostly liquid. Shrinkage is minimal, perhaps 0.5%. At 25 degrees, about half the cocoa butter has crystallized. Shrinkage is now 1%. The chocolate has pulled away slightly from the mold walls, but the gap is still too small to see. At 20 degrees, crystallization is complete. All the cocoa butter that will crystallize has done so. Shrinkage is 2%. The gap is now 0.1 to 0.2 millimeters, clearly visible if you look at the edge where chocolate meets mold. Temperature stability is another consequence of crystal structure. Enrober chocolate can sit at room temperature, 20 to 25 degrees, for months without melting or changing texture. This is because 25 degrees is well below Form V's melting point of 34 degrees. The chocolate remains solid and hard. The crystals don't melt. The structure doesn't change. If you measured the chocolate's hardness in January and again in June, you'd get the same value, about 500 newtons of force required to break it. However, if the chocolate is exposed to temperatures above 30 degrees, problems occur. At 30 degrees, the smallest Form V crystals begin to melt. These are crystals at the low end of the size distribution, perhaps 0.5 micrometers, that are less stable than average. When these small crystals melt, their molecules become liquid again. When the temperature drops back to 20 degrees, these molecules recrystallize, but not necessarily as Form V. Some recrystallize as Form 6. Form 6 is even more stable than Form V. It melts at 36 degrees instead of 34. This seems like an improvement, but Form 6 creates problems. It's harder than Form V with a brittle, waxy texture. It doesn't melt smoothly in the mouth. It feels grainy and unpleasant. Additionally, Form 6 crystals are larger than Form V crystals. The recrystallization process tends to produce fewer, larger crystals rather than many small ones. As Form 6 develops over days or weeks, the chocolate surface becomes rough. The increased roughness scatters light. The chocolate loses its gloss and develops a grayish-white coating. This is called fat bloom, cocoa butter that has recrystallized on the surface. Fat bloom is not harmful. The chocolate is still safe to eat, but it looks unappealing. Consumers often think bloomed chocolate has gone bad, though it hasn't. The only things that have changed are crystal form and surface texture. Preventing. Bloom requires temperature control throughout the supply chain. From the factory to the distribution center to the store to the consumer's home. The chocolate must never exceed 28 degrees. Above 28 degrees, even briefly, bloom becomes likely. This is challenging in warm climates. In a delivery truck on a hot, summer day, temperatures can exceed 40 degrees. Without refrigeration, chocolate blooms within hours. This is why chocolate is often shipped in refrigerated trucks, adding significant cost to distribution. The melting behavior of chocolate is precisely engineered. Form V chocolate begins to melt at 34 degrees. Human body temperature is 37 degrees. This means chocolate is solid at room temperature, but melts in your mouth. The 3-degree difference is deliberate. If chocolate melted at 30 degrees, it would melt in your hand before reaching your mouth. If it melted at 40 degrees, it wouldn't. It melt in your mouth at all. You'd have to chew it, and the texture would be unpleasant. The melting is endothermic. It absorbs heat. The latent heat of fusion for cocoa butter is 160 kilojoules per kilogram. When chocolate melts on your tongue, it draws heat from your mouth tissue. This creates a cooling sensation, a slight chill, as the chocolate melts. This cooling is part of chocolate's sensory appeal. The smoothness of melting combined with the cooling sensation creates a unique mouthfeel that consumers find pleasurable. Chocolate that doesn't melt properly, that stays solid or becomes grainy, lacks this appeal. The melting also releases flavor compounds. Chocolate contains over 600 different volatile organic compounds. Molecules light enough to evaporate at body temperature and drift into your nasal cavity where they're detected by olfactory receptors. These compounds include esters, fruity notes, aldehydes, nutty notes, ketones, buttery notes, pyrazines, roasted notes, and alcohols, floral notes. Each contributes to chocolate's complex flavor profile. 3,5-trimethylpyrazine gives a roasted, nutty note. Its concentration in dark chocolate is about 0.5 parts per million, but it's highly aromatic. The human nose can detect it at concentrations as low as 0.01 parts per million. Benzaldehyde gives an almond-like note. Its concentration is about 0.3 parts per million. It's formed during roasting, when proteins break down and react with sugars. Linalool gives a floral note, almost rose-like. Its concentration is about 0.1 parts per million. It's present in the cocoa bean naturally, but increases during fermentation. These compounds are locked in the solid chocolate. The triglyceride crystal structure traps them in tiny pockets between crystals. When the chocolate melts, these pockets open and the volatile compounds escape. This is why chocolate flavor seems to bloom in your mouth. The melting releases aromatics that weren't perceptible when the chocolate was solid. If you smell solid chocolate, you detect some aroma, but it's weak. If you let chocolate melt on your tongue and then exhale through your nose, the aroma is intense. The texture of melting chocolate is equally important. As the crystals melt, the chocolate transitions from solid to liquid. This transition happens over a narrow temperature range, from 34 to 37 degrees, just 3 degrees. This narrow melting range creates a sharp transition. One moment the chocolate is solid, the next it's liquid. There's no mushy intermediate state. This clean transition is characteristic of pure substances with uniform crystal structure. Compare this to butter, which melts over a wide temperature range, from 28 to 36 degrees, an 8-degree span. Butter feels mushy as it melts because different triglycerides in butter melt at different temperatures. The high-melting triglycerides remain solid, even as low-melting ones become liquid. Chocolate's uniform composition, cocoa butter is about 80% symmetric triglycerides with similar melting points, creates uniform melting. All the crystals melt at approximately the same temperature, creating that sharp, solid to liquid transition. This clean melting is one reason chocolate feels so satisfying in the mouth. The transformation from solid to liquid is complete and sudden. It's not gradual or partial. This decisiveness in texture change is part of what makes chocolate texturally superior to other confections. To understand tempering at the deepest level, we must examine individual molecules. A cocoa butter molecule is approximately 2.5 nanometers long. It consists of 3 parts, a glycerol backbone and 3 fatty acid chains. The glycerol backbone is a 3-carbon molecule with 3 hydroxyl groups. Each carbon atom is bonded to hydrogen and to a hydroxyl group, oxygen bonded to hydrogen. The 3 hydroxyl groups are the attachment points for fatty acids. Each hydroxyl group forms an ester bond with a fatty acid. An ester bond is formed when the hydroxyl group reacts with the carboxyl group of the fatty acid, releasing a water molecule. The 3 fatty acids extend from the glycerol like prongs on a fork. In cocoa butter, the fatty acids are primarily stearic acid, palmitic acid, and oleic acid. Stearic acid has 18 carbon atoms in a straight chain. Every carbon is bonded to 2 hydrogens, except the first carbon, which is part of the carboxyl group. The stearic acid chain is saturated. Every carbon-carbon bond is a single bond. This allows the chain to be perfectly straight. The straightness is important because straight chains can pack together tightly in crystals. Palmitic acid has 16 carbon atoms, also in a straight, saturated chain. It's similar to stearic acid, just 2 carbons shorter. Oleic acid has 18 carbon atoms with 1 double bond between carbon 9 and carbon 10. This double bond creates a kink. The chain bends by about 30 degrees at that point. The kink prevents tight packing, making oleic acid-containing triglycerides less orderly. The specific combination matters. Most cocoa butter triglycerides have one of these structures: palmitic oleic stearic, POS, stearic oleic stearic, SOS, or palmitic oleic palmitic, POP. These 3 types account for approximately 80% of cocoa butter. In POS, the palmitic acid is at position 1 of the glycerol, the top position, oleic at position 2, the middle, and stearic at position 3, the fuel, bottom. This specific arrangement is called a positional isomer. Same components, different positions. SOS has stearic acids at positions 1 and 3, with oleic in the middle. This symmetric arrangement, same fatty acid on both ends, makes SOS particularly good at forming regular crystals. About 30% of cocoa butter is SOS pop, is similar but with shorter palmitic acids on the ends. About 20% of cocoa butter is pop. POS, with one palmitic and one stearic, makes up about 30%. The remaining 20% consists of other combinations, stearic-oleic-oleic, SOO, palmitic-palmitic-oleic, PPO, and so on. This variety creates complexity in the crystallization behavior. Different triglycerides crystallize at slightly different temperatures and prefer slightly different crystal structures. When liquid, these molecules move randomly. At 50 degrees, each molecule has enough thermal energy to overcome attractive forces from neighboring molecules. They tumble and slide past each other freely. The liquid flows. The motion is called Brownian motion, random movement caused by thermal energy. A molecule might move forward 10 nanometers, then backward 5, then sideways 8. Over time, it wanders throughout the liquid, eventually exploring every part of the container. The speed of this motion depends on temperature. At 50 degrees, a triglyceride molecule moves at an average speed of about 300 meters per second, about the speed of sound in air. This seems fast, but the molecule constantly collides with neighbors, so its net displacement is small. The attractive forces are van der Waals forces, weak interactions between molecules caused by temporary fluctuations in electron distribution. Electrons are constantly moving around atomic nuclei. At any instant, there might be more electrons on one side of a molecule than the other, creating a temporary dipole. One end slightly negative, the other slightly positive. This temporary dipole induces a dipole in a nearby molecule. The negative end repels electrons in the neighbor, making that end positive. The two dipoles attract each other. The force is weak, about 4 kilojoules per mole, but it's present between all molecules, all the time. For cocoa butter triglycerides, the van der Waals force between two molecules is about 40 zeptojoules. That's 40 times 10 to the minus 21 joules. This is an incredibly small number. But with billions of molecules in contact, the total force is significant. At 50 degrees, the thermal energy per molecule is about 60 zeptojoules. This is greater than the van der Waals force, so molecules can break free from their neighbors. The liquid flows freely. As temperature decreases, thermal energy decreases. At 40 degrees, thermal energy is about 52 zeptojoules, closer to the van der Waals force, but still greater. Molecules still move freely, but slightly more slowly. At 35 degrees, thermal energy is about 48 zeptojoules, now slightly less than the van der Waals force for some molecular pairs. Molecules spend brief moments attached to neighbors before thermal motion breaks them apart. Small clusters form, perhaps 10 or 20 molecules aligned parallel to each other. These clusters are transient. They form and break apart in milliseconds, but they represent the beginning of order emerging from disorder. At 34 degrees, the melting point of form V, the thermal energy is about 47 zeptojoules. This is low enough that stable clusters can form. Once a cluster reaches a critical size, about 100 molecules, it becomes more stable to add molecules than to break them off. The cluster grows spontaneously. This critical size is determined by thermodynamics. Small clusters have a high surface-to-volume ratio. Most molecules in the cluster are on the surface, where they have fewer neighbors and thus weaker total van der Waals forces. The cluster is unstable. Large clusters have a low surface-to-volume ratio. Most molecules are in the interior, surrounded by neighbors, with strong total van der Waals forces. The cluster is stable. The transition happens at about 100 molecules. Below this size, thermal energy is likely to break the cluster apart. Above this size, van der Waals forces hold it together and it grows spontaneously. The growth follows specific rules. Molecules attach most easily to the crystal's flat faces. The surfaces, where the fatty acid chains are aligned parallel to the surface. A molecule approaching such a face can slide into place and align its chains with those already in the crystal. Attachment to the edge or corner positions is less favorable. At an edge, the incoming molecule has neighbors on only 2 sides instead of 3. At a corner, it has neighbors on only 1 side. These positions are less stable, so attachment is less likely. This preferential growth creates flat, plate-like crystals. Form V crystals grow fastest in the directions parallel to the fatty acid chains and slowest in the direction perpendicular to them. The result is a crystal approximately 10 times wider than it is thick. A typical Form V crystal might be 1 micrometer wide and 0.1 micrometers thick. It looks like a tiny playing card. Under a microscope with polarized light, these crystals appear as bright rectangular flakes against a dark background. The crystals don't grow in isolation. As one crystal grows, it depletes the liquid around it of molecules. The concentration of triglycerides in the liquid near the crystal becomes lower than the concentration farther away. This creates a concentration gradient, a smooth variation, in concentration from low near the crystal to high far from it. Molecules naturally diffuse down concentration gradients from high concentration to low. So molecules diffuse toward the growing crystal. The diffusion rate depends on temperature and viscosity. Diffusion in liquids is described by the Stokes-Einstein equation. The diffusion coefficient equals thermal energy divided by 6p times viscosity times molecular radius. At 31 degrees in chocolate with 2000 centipoise viscosity, a triglyceride, molecule, radius about 1 nanometer, has a diffusion coefficient of about 1 times 10 to the minus 11 square meters per second. This means in 1 second, a molecule diffuses an average distance of about 1 micrometer. This diffusion rate limits crystal growth. Even if the crystal surface could incorporate molecules instantly, growth would still be limited by how fast molecules arrive. The maximum growth rate is determined by the diffusion coefficient and the concentration gradient. Under typical conditions, the maximum growth rate is about 0.1 micrometers per second. In practice, growth is slower, about 0.01 micrometers per second. Because surface incorporation isn't instantaneous, molecules must orient correctly before attaching. A molecule approaching the crystal surface tumbles randomly. Most of the time, it's oriented incorrectly. Its fatty acid chains aren't parallel to those in the crystal. When it hits the surface at a wrong angle, it bounces off. Only when it approaches, with the right orientation, chains parallel to the crystal, can it attach. The probability of correct orientation is about 1 in 1,000. So out of 1,000 molecules hitting the surface, only 1 attaches. The other 999 bounce off and try again. This selectivity ensures crystal quality. If molecules could attach at any orientation, the crystal would be disordered and weak. By accepting only correctly oriented molecules, the crystal maintains perfect order, every molecule aligned the same way. The growth continues until the liquid is depleted, or until the crystals touch each other. When crystals touch, interesting things happen. If they're aligned the same way, the same crystal form, same orientation, they can merge, growing together into a larger crystal. If they're aligned differently, different orientations or different crystal forms, they don't merge. Instead, they form a grain boundary, an interface where the 2 crystal structures meet. Grain boundaries are weak points in the crystal network. When you bite into chocolate, it fractures at grain boundaries. The snap sound is created by fractures propagating along these boundaries. Well-tempered chocolate has many small grains, billions, of tiny Form V crystals. So grain boundaries are evenly distributed. The fracture can propagate anywhere, creating clean breaks. Poorly tempered chocolate has fewer, larger grains. Grain boundaries are fewer and unevenly distributed. Fractures wander around trying to find boundaries, creating irregular breaks and crumbly texture. The crystal network in well-tempered chocolate is about 60% crystal and 40% liquid cocoa butter trapped in the spaces between crystals. This trapped liquid contains dissolved sugar and cocoa solids, creating the chocolate's flavor. When you bite into chocolate, you're fracturing this crystal network. The force required depends on network strength. Well-tempered chocolate, with small uniform form V crystals, requires about 500 newtons of force to break, roughly equivalent to supporting a 50-kilogram weight. This force breaks bonds throughout the crystal network. The energy required is about 1,000 joules per square meter of fracture surface. This is called the fracture toughness. For a 1 square centimeter piece of chocolate, 3 millimeters thick, breaking it releases about 0.03 joules of energy. This energy becomes heat, warming the chocolate slightly. Sound, the snap, and kinetic energy, the two pieces moving apart. Most becomes kinetic energy. The pieces fly apart at a few centimeters per second. The chocolate factory operates 24 hours a day, 7 days a week, producing 20 tons of finished chocolate products every day. The facility covers 5,000 square meters on a single floor. The ceiling is 6 meters high to accommodate the enrober and other tall equipment. The temperature in the factory is controlled at 20 degrees Celsius year-round. This is not primarily for worker comfort, it's for chocolate quality. If the ambient temperature varies, the chocolate's behavior changes. Tempering windows shift, cooling rates fluctuate. Viscosity changes, defects appear. The temperature control is achieved by a large HVAC system, heating, ventilation, and air conditioning. The system has 20 tons of cooling capacity, enough to remove 70 kilowatts of heat. In summer, when outside temperatures reach 35 degrees, the system runs continuously to maintain 20 degrees inside. The system also heats in winter. When outside temperatures drop to 5 degrees, heaters activate to maintain 20 degrees. The heating capacity is 100 kilowatts, greater than the cooling capacity, because heating a large building requires more energy than cooling it. The humidity is controlled at 50% relative humidity. This is measured by hygrometers, sensors that detect moisture in the air. If humidity drops below 45%, humidifiers activate, spraying fine water mist into the air handling system. If humidity rises above 55%, dehumidifiers activate, condensing water out of the air, too dry, and static electricity builds up. Cocoa powder has low electrical conductivity, so when it rubs against plastic or metal surfaces, electric charge accumulates. If charge builds up enough, you get sparks, visible discharges that can ignite cocoa powder dust, creating a fire or explosion hazard. 2. Humid, and moisture condenses on chocolate surfaces. Water droplets form, dissolving sugar from the surface. When the droplets evaporate, the dissolved sugar recrystallizes in irregular patterns, creating sugar bloom, white spots that look like mold but aren't. The factory receives cocoa butter in 25-kilogram blocks. These blocks are solid at room temperature, hard like paraffin wax. They're wrapped in polyethylene film and packed in cardboard boxes for shipping. The cocoa butter comes from a processing facility where cocoa beans have been roasted, winnowed, ground, and pressed. The beans arrive at the processing facility as fermented dried beans from cocoa farms in Ghana, Ecuador, or Ivory Coast. First, they're roasted at 120 degrees Celsius for 30 minutes. Roasting develops flavor through Maillard reactions, chemical reactions between amino acids and sugars that create hundreds of flavor compounds. It also dries the beans, making the shells brittle. Next, they're winnowed. The shells are cracked and blown away by air currents, leaving just the nibs, the inner meat of the bean. The nibs are ground in a mill, creating cocoa liquor, a thick paste that's about 55% cocoa butter and 45% cocoa solids. The liquor is pressed using hydraulic presses that apply 400 bar of pressure. This squeezes out the cocoa butter, which flows out as liquid and solidifies into blocks. What remains is a hard cake of cocoa solids, which is ground into cocoa powder. The cocoa butter blocks are stored in a temperature-controlled warehouse at 18 degrees until needed. At this temperature, the cocoa butter is solid but not brittle. It can be handled without breaking. Sugar arrives in 1-ton bags, fine white crystals of pure sucrose extracted from sugarcane or sugar beets. The sugar crystal size is 200 micrometers on average, large enough to flow freely but small enough to dissolve easily. The sugar is stored in silos, tall cylindrical tanks 5 meters in diameter and 10 meters high. Each silo holds 200 tons. The silos are airtight to prevent moisture absorption. Humid air would cause the sugar to cake. The crystals would stick together in hard lumps that don't flow. Cocoa powder arrives in 25-kilogram bags. This is what remains after cocoa butter is pressed out. Pure cocoa solids ground to a powder with particles 20 to 30 micrometers in diameter. The powder is dark brown, almost black, with an intense chocolate aroma. Milk powder arrives for milk chocolate production. This is whole milk that has been spray-dried, sprayed as tiny droplets into a 200-degree airstream. The water evaporates instantly, leaving powder. The powder particles are hollow spheres about 50 micrometers in diameter, containing trapped air. The production process begins in the mixing room. Here, ingredients are combined according to formulas. For dark chocolate, 45% cocoa butter, 35% sugar, 20% cocoa powder. For milk chocolate, 30% cocoa butter, 40% sugar, 15% cocoa powder, 15% milk powder. The percentages are by weight. For a 1,000 kilogram batch of dark chocolate, that's 450 kilograms cocoa butter, 350 kilograms sugar, 200 kilograms cocoa powder. The ingredients are weighed precisely using load cells, sensors that measure weight by detecting how much a spring or beam deflects under load. The load cells are accurate to 0.1%. For a 450 kilogram weighing, the error is no more than 0.45 kilograms. The weighed ingredients are dumped into a mixer, a large vessel 2 meters in diameter and 1.5 meters high, with a rotating shaft that has paddle arms attached. The shaft rotates at 40 revolutions per minute. The paddles fold the ingredients together, creating a uniform mixture. The mixing takes 30 minutes. After 10 minutes, the ingredients are partially mixed. You can still see separate clumps of cocoa, powder, sugar, and cocoa butter. After 20 minutes, the mixture is more uniform but still has some streaks. After 30 minutes, it's completely uniform. Every sample taken from the mixer has the same composition. From the mixer, the blend goes to the refiner. The refiner consists of 5 steel rollers arranged vertically in a stack. Each roller is 1 meter long and 30 centimeters in diameter, weighing about 500 kilograms. The rollers rotate at different speeds, creating shearing forces between them. The first roller rotates at 50 revolutions per minute, the second at 150, the third at 300, the fourth at 600, the fifth at 1200. The chocolate mixture is fed onto the first roller as a thick paste. It adheres to the roller surface and is carried upward. At the gap between the first and second rollers, the mixture is pulled through. The gap is 200 micrometers. As the mixture passes through, particles larger than 200 micrometers are crushed between the rollers. The rollers are hard chrome-plated steel, harder than sugar crystals, so the crystals break rather than the rollers. The mixture then passes between the second and third rollers, where the gap is 100 micrometers. Particles larger than 100 micrometers are crushed. Then the third and fourth, gap 50 micrometers. Finally, the fourth and fifth, gap 25 micrometers. After passing through all 5 gaps, the largest particles in the chocolate are 25 micrometers. This is important because the tongue can detect particles larger than 30 micrometers as grittiness. The tongue has tactile receptors that can sense texture at this scale. Particles smaller than 25 micrometers feel smooth. They're too small for the tongue's receptors to detect individually. They blend together into a uniform, creamy texture. The pies. Refining generates significant heat. The shearing forces create friction, and friction creates heat. The chocolate exits the refiner at about 50 degrees, even though it entered at 40 degrees. This heat must be managed. If the chocolate gets too hot, it can develop off flavors. From the refiner, the chocolate goes to the conch. The conch is a large heated vessel 3 meters long, 1.5 meters wide, and 1 meter deep, with a rotating shaft that has heavy stone rollers attached. The process is called conching, named after the original shell-shaped vessels used in the 19th century by Rudolf Lindt, who invented the process in 1879. The rollers roll back and forth through the chocolate, creating intensive mixing and shearing. Conching serves several purposes. First, it reduces moisture content. The chocolate is heated to 60 degrees, and the surface is constantly renewed by the rolling action. Water evaporates from the surface into the air above. Moisture drops from 2% to 0.5% over the course of conching. Less moisture means better shelf life. Water supports bacterial and mold growth. Dry chocolate, below 1% moisture, is inhospitable to microorganisms and can be stored for years without spoiling. Second, conching develops flavor. The heat and mechanical action drive off volatile acids, acetic acid, propionic acid, and volatile aldehydes that create harsh, astringent flavors. These compounds have low boiling points, below 120 degrees, and evaporate preferentially. What remains is a smoother, mellower flavor profile. The chocolate tastes less acidic, less bitter, more rounded. Professional tasters describe well-conched chocolate as having harmonious or balanced flavor, compared to the raw or harsh flavor of unconched chocolate. Third, conching affects viscosity. The mechanical action coats sugar particles with cocoa butter. Sugar particles are hydrophilic, they attract water. Cocoa butter is hydrophobic, it repels water. When sugar particles are coated with cocoa butter, they no longer stick together as much. This reduces the apparent viscosity. Unconched chocolate might have a viscosity of 5,000 centipoise. After 24 hours of conching, it drops to 2,500 centipoise. After 48 hours, 2,000 centipoise. The chocolate flows more easily, making it easier to work with. Conching takes 12 to 72 hours depending on the chocolate type. Dark chocolate requires longer conching, 48 to 72 hours, to develop full flavor. The cocoa solids in dark chocolate contain many volatile acids that need time to evaporate. Milk chocolate requires less, 12 to 24 hours, because milk proteins contribute smoothness and mask harsh flavors. The proteins bind to volatile compounds, preventing them from reaching taste receptors. White chocolate, which contains no cocoa solids, requires the least conching, just 6 to 12 hours. It's conched primarily to reduce moisture and improve texture, not to develop flavor. After conching, the chocolate is liquid at 60 degrees. It's pumped to storage tanks, where it's held until needed for production. The tanks are jacketed vessels with heating elements in the walls. The chocolate is kept at 45 degrees, hot enough to stay liquid, cool enough that volatile flavors don't evaporate. The tanks are stirred continuously by slow rotating paddles, about 5 revolutions per minute. This prevents settling. Cocoa solids are denser than cocoa butter, 1,400 kmol M3 versus 900 kmol M3, and would settle to the bottom if not stirred. When production begins, chocolate is pumped from storage to the tempering machine. This is where our story began, the controlled heating and cooling that creates Form V crystals. After tempering, the chocolate goes to the enrober for coating products, or to molding machines for making chocolate bars. Molding machines are used when the chocolate itself is the product, not a coating. The machine consists of a hopper that holds tempered chocolate at 31 degrees and a series of molds that move on a chain conveyor. The molds are polycarbonate plastic, precision machined with cavities in the shape of chocolate bars. Each mold has 12 cavities. The cavity dimensions are exactly the dimensions of the finished bar, 10 centimeters long, 5 centimeters wide, 1 centimeter deep. The cavities are polished to a mirror finish, surface roughness less than 0.1 micrometers. This mirror finish is critical. The chocolate adopts the surface finish of the mold. If the mold is glossy, the chocolate is glossy. If the mold is rough, the chocolate is dull. The polishing is done using progressively finer abrasives, 80 grit, then 400 grit, then 1200 grit, then polishing compound. The molds are preconditioned to 10 degrees before filling. This is done by passing them through a cooling tunnel where cold air blows over them. The cold molds help the chocolate crystallize quickly when deposited. Tempered chocolate at 31 degrees is deposited into the molds by a depositor, a bank of pistons, one above each cavity. Each piston delivers exactly 50 grams of chocolate, the weight of 1 bar. The pistons are controlled by a programmable logic controller that ensures consistent weight. The filling accuracy is plus 0.5 grams. Out of 1,000 bars, 999 will weigh between 49.5 and 50.5 grams. This accuracy is required by regulations. The labeled weight must be accurate, or the manufacturer faces fines. After filling, the molds vibrate on a vibrating table for 5 seconds. The table vibrates at 60 Hz, 60 vibrations per second. This vibration removes air bubbles trapped in the chocolate. Air bubbles form when chocolate is poured. The falling stream of chocolate traps air, creating bubbles that rise to the surface. But some bubbles get trapped in corners or under ledges where they can't escape. Vibration helps them escape. The vibration liquefies the chocolate slightly. It reduces viscosity by breaking the weak bonds between particles. The bubbles can now move more easily and rise to the surface where they pop. Without vibration, finished, bars would have visible holes or voids on the surface, defects that make the product unsaleable. The filled molds enter a cooling tunnel 20 meters long, refrigerated to 8 degrees. The molds move through at 1 meter per minute, spending 20 minutes in the tunnel. During this time, the chocolate crystallizes completely. The cooling follows a specific profile. In the first 5 minutes, the air temperature is 12 degrees. The chocolate cools from 31 to 24 degrees. Most crystallization happens in this zone. In the next 10 minutes, the air temperature is 8 degrees. The chocolate cools from 24 to 16 degrees. Crystallization is mostly complete. This zone is mainly for solidification. In the final 5 minutes, the air temperature is 4 degrees. The chocolate cools from 16 to 12 degrees, making it cold enough to release from the mold easily. At the tunnel exit, the molds are inverted over a conveyor. A mechanical vibrator taps each mold 3 times. Sharp raps that dislodge the chocolate bars. The bars fall out onto a padded conveyor belt. The release is clean because the chocolate has shrunk 2% during crystallization, creating a gap between chocolate and mold. The bars fall smoothly, landing right side up on the belt. The glossy surface that was against the mold is now the top surface, perfectly smooth and reflective. The bars are wrapped immediately while still cold, at 12 degrees. Wrapping is done by a machine that folds foil and paper around the bar at a rate of 200 bars per minute. The machine picks up each bar with suction cups, places it on a sheet of foil, folds the foil around it, then adds an outer paper wrapper with printing. The foil is aluminum, 20 micrometers thick. It's impermeable to moisture, oxygen, and light, all things that can damage chocolate. The foil creates a complete barrier, sealing the chocolate from the environment. The paper wrapper is printed with the brand name, flavor, weight, ingredients, and barcode. The printing is done using flexographic printing, raised rubber plates that transfer ink onto the paper. 4 colors are used: cyan, magenta, yellow, and black, which combine to create full-color images. The wrapped bars are packed into boxes, 24 bars per box. The boxes are corrugated cardboard, 30 centimeters long, 20 centimeters wide, 15 centimeters high. They're assembled automatically by a case erector, a machine that takes flat cardboard blanks, folds them into boxes, and tapes the bottom flaps. The boxes are filled by a case packer, a machine with a robotic arm that picks up bars from the conveyor and places them in the box in a neat 4x6 pattern. When full, the box moves to a case sealer that folds the top flaps and applies tape. The filled boxes are labeled with shipping information: destination, order number, production date. The labels are printed and applied automatically by a print and apply system that reads order data from a computer and prints the correct label for each box. The boxes are stacked on pallets, wooden platforms 1.2 meters square. Each pallet holds 120 boxes, stacked in 6 layers of 20 boxes each. The stack is 1.8 meters high and weighs about 1,500 kilograms, 1.2 tons of chocolate per pallet. The pallets are wrapped with stretch film, clear plastic film that's stretched as it's wound around the stack. The film holds the boxes together and prevents them from shifting during transport. The wrapping is done by a pallet wrapper, a machine with a turntable that rotates the pallet while a film carriage circles around it. The wrapped pallets are moved to the warehouse by forklifts. The warehouse is temperature controlled at 18 degrees, cool enough to prevent melting or bloom, warm enough that the chocolate doesn't become brittle. The warehouse holds up to 500 pallets, 600 tons of chocolate, stored in racks 6 meters high. The pallets are retrieved by forklifts when orders are placed, loaded onto trucks, and shipped to distribution centers. From the distribution centers, the chocolate goes to stores, from stores to consumers, and eventually to mouths, where it melts and releases its flavor and creates that moment of satisfaction that makes all the effort worthwhile. The pursuit of perfect chocolate has occupied chocolatiers for 200 years. Every aspect has been studied, measured, and optimized. The result is chocolate that's consistent, reliable, and exquisite. But this perfection is fragile. It depends on maintaining precise conditions at every step. A temperature deviation of 2 degrees during tempering creates form A4 instead of form V. A humidity spike during storage creates sugar bloom. A rough vibration during transport creates internal cracks. The chocolate maker's challenge is controlling these variables across time and space. From the factory floor to the distribution center, to the store shelf, to the consumer's hand, nothing can go wrong. Modern technology helps. Temperature sensors with 0.1 degree accuracy report readings every second. Humidity monitors with 1% precision track moisture levels continuously. Automated systems adjust heating and cooling in real time based on feedback from dozens of sensors. Quality. Control instruments measure gloss using gloss meters, devices that shine light at a standard angle onto the chocolate surface and measure how much reflects back. Well-tempered chocolate reflects 80% of incident light. Poorly tempered chocolate reflects only 40%. Hardness is measured using a penetrometer, a device that pushes a probe into the chocolate surface with a known force and measures how far the probe penetrates. Hard chocolate, form V, penetrates only 2 millimeters. Soft chocolate, form IV, penetrates 5 millimeters or more. Crystal size is measured using X-ray diffraction. X-rays are beamed at the chocolate and scatter off the crystal lattices. The scattering pattern reveals the crystal structure and size. Form V crystals produce a characteristic pattern. Sharp peaks at specific angles that correspond to the 0.46 nanometer spacing of molecules. These instruments provide objective measurements that remove human subjectivity. But ultimately, chocolate quality depends on human judgment. An experienced chocolatier can assess chocolate by sight, touch, and sound. They can see subtle differences in gloss that indicate crystal size. They can feel differences in hardness that reveal crystal form. They can hear the quality of the snap when the chocolate breaks, a sharp, clean crack versus a dull thud. This expertise takes years to develop. A master chocolatier has made chocolate thousands of times, failed thousands of times, learned from each failure. They've tempered chocolate in hot weather and cold, with fresh cocoa butter and old, with different sugar sources and different equipment. They've seen every type of defect. Fat bloom, sugar bloom, whitening, softening, graininess, crumbliness. They know what caused each defect and how to prevent it. This knowledge is partly documented, written in procedures and specifications, but partly tacit, residing only in the expert's mind. They've developed an intuition, an ability to sense when something is wrong, even if measurements say everything is fine. They might notice that the chocolate flowing from the tempering tank looks slightly different, more viscous, less glossy, even though the temperature reads exactly 31.0 degrees. They investigate. They take a sample and let it solidify. They examine the surface, check the snap, feel the texture. They discover that the chocolate is slightly over-tempered, too many seed crystals, making it thick and dull. They adjust the seeding rate downward by 0.2%, and the problem is solved. This kind of subtle adjustment, based on observation rather than measurement, is what separates good chocolate from great chocolate. The science provides the foundation, the knowledge of crystals and temperatures and viscosities. But the art provides the refinement, the subtle adjustments that transform good chocolate into exceptional chocolate. The chocolatier knows that perfection is not a destination, but a practice. Every batch is an opportunity to do better. Every defect is a lesson. Every success is temporary. Tomorrow brings new challenges, new batches, new opportunities to fail or succeed. They know that chocolate is not just chemistry and physics, though it is those things. It's also craft. It's the skill developed over years of repetition. It's the judgment honed by thousands of decisions. It's the pride in making something well. They know that chocolate making is ultimately about people. About the farmer who grows cocoa, about the roaster who develops flavor, about the factory worker who operates the machines, about the chocolatier who monitors the tempering, about the consumer who tastes the finished product. All these people are connected through chocolate. The farmer's work becomes the chocolatier's raw material. The chocolatier's work becomes the consumer's pleasure. The consumer's satisfaction justifies the farmer's labor. The circle is complete. As you drift towards sleep, imagine the chocolate factory running through the night. The tempering machines humming at 31 degrees, the enrober curtains falling in laminar flow, the cooling tunnels refrigerating at 10 degrees, the conveyors moving at 10 meters per minute, the wrappers folding at 200 bars per minute, thousands of chocolate pieces flowing through the system every hour, each one tempered to the same specification, each one cooled at the same rate, each one wrapped with the same precision, each one packaged with the same care. The process never stops. The chocolate keeps flowing. Form V crystals keep growing at 0.01 micrometers per second. The glossy surfaces keep emerging from the molds at 80% reflectivity. The perfect snap keeps happening when the bars break at 500 newtons of force. Temperature holds at 31 degrees plus or minus 0.5 degrees. The cooling rate maintains 1 degree per minute, plus or minus 0.2 degrees per minute. The viscosity stays at 2000 centipoise, plus or minus 100 centipoise. The crystal size remains at 1.0 micrometers, plus or minus 0.2 micrometers. Every parameter controlled, every variable measured, every process optimized. All to create chocolate that snaps cleanly, melts smoothly, and tastes exquisite. And tomorrow, somewhere, someone will unwrap a bar of chocolate. They'll break off a piece. They'll hear the snap, that sharp, clean sound of crystal lattices fracturing at 1,000 meters per second. They'll see the gloss, light reflecting at 80% efficiency from billions of perfectly aligned Form V crystals. They'll place the chocolate on their tongue. They'll feel it melt, the solid transforming to liquid as temperature rises from 20 to 37 degrees, crossing the Form V melting point of 34 degrees. They'll taste the flavor. 600 volatile compounds released as the crystal structure dissolves, drifting into the nasal cavity and triggering olfactory receptors. They won't think about tempering or crystals or viscosity. They won't think about the precise temperatures maintained throughout production. 50 degrees for melting, 27 for cooling, 31 for working. They won't think about the cooling rates or the seeding process or the 6 crystal forms. They won't think about the molecular structure, the triglycerides with their glycerol backbones and fatty acid chains, the 0.46 nanometer spacing in the E Form V lattice, the van der Waals forces holding molecules together. They'll simply experience the pleasure. The texture, smooth and creamy as the chocolate melts. The flavor, rich and complex with notes of roasted nuts and dark fruit. The satisfaction, that deep contentment that comes from eating something made well. But that pleasure depends entirely on the invisible architecture of crystal structure, on the billions of Form 5 crystals arranged in perfect order, on the tempering process that created them at 31 degrees, on the enrober curtain that coated them in laminar flow, on the cooling tunnel that solidified them at 1 degree per minute. The entire industrial system exists to deliver that moment of pleasure. The factories running day and night, the tempering machines cycling through their precise temperature programs, 50 to 27 to 31 degrees. The enrober curtains falling at 2 meters per second, the cooling tunnels maintaining 10 degrees plus or minus 1 degree, all of it to create perfect chocolate. Glossy at 80% reflectivity, hard at 500 newtons breaking force, snapping cleanly with fractures propagating at 1,000 meters per second, melting smoothly at 34 to 37 degrees. The chocolate maker knows this. They understand that their work is invisible to the consumer. The consumer sees only the finished product, a bar of chocolate wrapped in foil and paper. They don't see the 72 hours of conching at 60 degrees, the 5-roller refining to 25 micrometers, the temperature curve of tempering, 50 to 27 to 31, the controlled cooling at 1 degree per minute. But the chocolate maker doesn't need recognition. They find satisfaction in the work itself, in the precision, maintaining 31 degrees within 0.5 degrees for hours, in the consistency, every batch meeting the same standard of 1.0 micrometer crystals, in knowing that every bar, every piece, every bite will deliver the same experience. They find satisfaction in the science, in understanding how triglyceride molecules arrange themselves into crystal lattices based on fatty acid chain length, how form V differs from form IV by just 0.02 nanometers in molecular spacing, how temperature controls which form develops through thermodynamic favorability, how cooling rate affects crystal size through nucleation and growth kinetics. They find satisfaction in the craft, in adjusting the tempering curve based on the chocolate's behavior, adding seeding if crystals are too few, reducing seeding if too many, in recognizing when the gloss looks slightly wrong, 80% reflectivity versus 85%, in hearing the difference between good snap and excellent snap, the sharp crack versus the perfect crystalline fracture. This knowledge has been accumulated over generations. Rodolphe Lindt invented conching in 1879. Daniel Peter added milk powder in 1875 to create milk chocolate. Coenraad van Houten developed the cocoa press in 1828. Each innovation built on previous knowledge, adding refinement, improving quality. Each chocolatier learns from the previous generation, adds their own observations, passes the knowledge forward. The result is a deep understanding, part science, part art, part intuition, that transforms cocoa beans into chocolate. As the night deepens and sleep approaches, the chocolate factory continues its work. The tempering tank holds 500 kilograms at exactly 31.0 degrees. The stirrer rotates at 20 revolutions per minute. The temperature sensors read 31.0, 31.1, 31.0 degrees, cycling around the set point with a variance of plus or minus 0.5 degrees. Inside that tank, billions of form V crystals float in liquid cocoa butter at 2,000 centipoise viscosity. Each crystal is a seed of perfection, each one a template for the molecular order that creates great chocolate. Each one growing at 0.01 micrometers per second, molecule by molecule. The crystals grow slowly, layer by layer, triglyceride by triglyceride. The growth is invisible to the eye, but profound in its consequences. These growing crystals are the difference between mediocre chocolate and exceptional chocolate. The tempering operator checks the temperature display, 31.0 degrees. Perfect. They dip a spatula into the tank and withdraw a small sample. They spread the chocolate on a cold marble slab and wait 3 minutes. The chocolate solidifies. The operator examines the surface. It's glossy. Light reflects uniformly at 80% efficiency. They tap it with their knuckle. It's hard. The sound is sharp, indicating proper crystal structure. They bend a corner. It snaps cleanly at 500 newtons with no crumbling. The fracture propagates straight through at 1,000 meters per second. Perfect temper. Form V crystals at 1.0 micrometers. The operator nods and returns to monitoring the system. The chocolate flows from the tempering tank to the enrober at 20 liters per minute. The curtain falls at 2 meters per second. The belt moves at 10 meters per minute. The blower blows at 30 meters per second. The cooling tunnel cools at 10 degrees. Everything proceeds as designed. The system is stable. The chocolate is perfect. The night shift continues until dawn, when the day shift will arrive and the cycle will begin again. But for now, in the quiet hours before morning, the machines hum their steady rhythm. The chocolate flows at 20 liters per minute. The crystals grow at 0.01 micrometers per second. The temperature holds at 31 degrees plus or minus 0.5 degrees, and somewhere in that precise temperature, in that controlled environment, in those billions of perfectly aligned form V crystals growing at 0.46 nanometer molecular spacing, is the essence of chocolate making, the invisible architecture that creates visible pleasure, the molecular order that produces sensory delight, the science that becomes art, the process that becomes product, the crystal that becomes chocolate. Sleep now, knowing that across the world, chocolate is being made. Tempered perfectly at 31 degrees, cooled precisely at 1 degree per minute, crystallized completely into form V at 1.0 micrometers, ready to deliver that moment of pleasure, the snap at 500 newtons, the gloss at 80% reflectivity, the smooth melting. At 34 to 37 degrees, that makes chocolate more than food. That makes it an experience, a memory, a moment of perfection in an imperfect world. The tempering machines run on. The form V crystals grow at 0.01 micrometers per second. The chocolate flows at 20 liters per minute. And tomorrow, the work continues, as it has for 200 years, as it will for 200 more. The endless pursuit of perfect chocolate, the art and science of crystallization. The temperature held at exactly 31 degrees, plus or minus 0.5 degrees, forever.